Welcome to our deep dive today, where we're going to be tackling a period in the universe's history that has scientists really scratching their heads.
Sounds fun.
Yeah, it's going to be a good one, I think. We're talking about the epoch of reionization, and our main source for today is the Knowable magazine article, When Everything in the Universe Changed.
I like it.
Yeah, it's a good one.
Hatchy.
And one of the things I found really interesting about this
Okay.
is this idea of a photon budget crisis,
Yeah.
which I'd never heard of before.
It's a good way to put it.
So I'm really excited to kind of unpack this whole thing with you.
Yeah, let's do it. I think what's so interesting about this is we know when reionization happened, but it's this question of how. So we're looking back at the early universe and we're seeing all these galaxies that are forming and all these photons being produced. But the numbers just don't add up.
Right.
We're missing something.
It's like we know the answer to the equation, but we can't figure out the steps to get there.
Exactly, like trying to bake a fake, and somehow you end up with twice as much batter as you started with.
Yeah, where'd that extra batter come from?
Right.
Okay, so let's back up a little bit, because we're talking about the epoch of reionization, which happened millions of years after the Big Bang.
Right.
So paint a picture for our listener. What did the universe even look like back then?
Well, picture this. You've got no stars, no galaxies.
Okay.
Just this vast expanse of dark, cold hydrogen gas.
It's hard to even imagine that.
It is.
It's so different from what we see today when we look up at the night sky.
Right. It's like the lights are out, and we're waiting for someone to flip the switch.
Yeah, so how do we go from this, kind of cosmic void to the universe as we know and love it today?
So around 100 million years after the Big Bang, the first stars start to form, and this is what we call cosmic dawn.
Cosmic dawn, I like that.
Yeah.
So these first stars are kind of like the pioneers venturing into this vast, unexplored territory.
Exactly. They're massive. They're mostly made of hydrogen and helium, and they start the process of nuclear fusion.
So that's what makes them so special. They're like the first ones to really start
Yeah.
changing the makeup of the universe.
Right. And as they burn through their fuel, they're emitting intense ultraviolet radiation.
Oh, so it's like they're turning on a giant UV lamp in a dark room.
Yeah, a really, really powerful one. And that light, that UV radiation starts to interact with all that neutral hydrogen gas.
Okay, and when you say interact, what does that mean exactly?
It starts to ionize it.
Ionize.
So it strips the electrons away from the hydrogen atoms.
Okay, so we're going from neutral hydrogen to ionized hydrogen.
Exactly, and that's happening on a massive scale across the universe. And that's the epoch of reionization.
And that's where the photon budget crisis comes into play.
Yeah, basically.
It's like we're seeing too much ionization for the number of stars we actually observed.
We have the James Webb Space Telescope, or JWST. It's been giving us these incredible views of these really early galaxies.
Oh, and I remember reading about these universe-breaker galaxies. They're ahead of schedule.
Yeah, way ahead of schedule.
But even with these unexpectedly bright and massive galaxies, there's still not enough radiation to explain the speed at which reionization happened.
That's the problem.
So it's like we're missing a source of radiation.
Right, we are. And then there's another twist to the story.
What's that?
Supermassive black holes.
I always picture them as these giant cosmic vacuum cleaners.
Pretty good analogy.
Just sucking up everything in sight.
And what's crazy is that the JWST has found evidence of these supermassive black holes forming way earlier than we ever thought possible.
Hold on. So we've got universe-breaker galaxies pumping out more radiation than expected.
Yep.
And we've got supermassive black holes showing up early to the party. Aren't both of those contributing to reionization?
You'd think so, right?
Yeah, shouldn't that solve our photon budget crisis?
It should, but even with all of that, the numbers still don't quite line up.
So we're still missing something.
Yeah, there's still a gap between the amount of ionizing radiation we can account for and the speed at which the universe went from being neutral to ionized.
It's like a real cosmic detective story.
It is.
We know what happened. We've got all these clues, but we can't quite crack the case yet.
But we're getting closer.
I love it.
And luckily, scientists are clever. They're coming up with all sorts of ingenious ways to try and solve this.
Okay, well, that's what I want to dig into next.
Let's do it.
What are some of the tools and techniques that are giving us more clues about this period in the universe's history?
Well, one really fascinating approach is to actually look for clues in the hydrogen itself, in the neutral hydrogen.
So like the stuff that was being ionized.
Exactly.
Okay, but how do you even do that?
So scientists are using radio telescopes to try to detect a very specific signal that neutral hydrogen emits. It's called the 21-centimeter radio signal.
Okay, wait a minute. How can we even detect a signal from hydrogen that existed billions of years ago?
Well, it's tricky.
especially when it's supposed to have all been ionized during this period.
It's not all gone. Remember, reionization wasn't instantaneous?
Oh, right. It happened gradually.
Right, over hundreds of millions of years. So there were still little pockets of neutral hydrogen kind of scattered throughout the universe as this process was unfolding.
So it's the signal from those pockets that we're trying to pick up.
Right.
Like trying to hear a whisper from across a crowded room.
Yeah, a really faint whisper.
And it's been traveling for billions of years.
Billions of years.
Okay, so what kind of radio telescopes are up to this challenge?
So one project that's doing some really incredible work is called the Hydrogen Epoch of Reionization Array,
Okay.
or HERA for short.
HERA, okay.
And it's located in South Africa, and it's this huge array of radio antennas.
I was looking at some pictures of it, and it looks almost deceptively simple,
It does.
especially compared to something like the James Webb Space Telescope, with its sleek, futuristic design.
Yeah, but the science that HERA is doing is just as groundbreaking. It's incredibly difficult to detect this signal. It's like trying to hear someone whisper a secret at a rock concert.
That's a good analogy.
Yeah.
So HERA's not the only project
No.
looking for this 21-centimeter signal?
There's also the EGS experiment,
Okay.
which stands for Experiment to Detect the Global Epoch of Reionization Signature.
That's a mouthful.
It is. Scientists love their acronyms.
Okay, so what's so special about EGS?
Well, the EGS team actually claimed to have detected the signal back in 2018.
Wow, so they actually heard the whisper.
They think so.
But was it what they were expecting to hear?
That's where things get interesting.
Okay,
The signal they detected was much stronger than anyone anticipated.
okay.
That implies that the hydrogen gas back then was much colder than our current models predict.
So not only do we have a photon budget crisis, but we've also got unexpectedly cold hydrogen.
It's a mystery.
Yeah, what are we to make of this?
It's caused a lot of debate. Some researchers are skeptical, wondering if maybe there were errors in the data or contamination from other sources.
So like maybe they weren't really hearing it
Exactly.
what they thought they were hearing.
Right.
But some people are taking it seriously
They are.
and trying to come up with explanations.
And some of those explanations are pretty out there.
Oh, like what?
We're talking about possible interactions between dark matter and ordinary matter. Maybe even interactions between different types of dark matter.
Wow. So we're going down the dark matter rabbit hole now.
Yeah, it's a deep one.
So it's like one mystery leads to another,
It does.
and it makes you realize just how much we still don't know
Right.
about the universe.
Absolutely.
But that's what makes it so exciting.
It does.
So we've got the James Webb Space Telescope giving us these incredible images of early galaxies. We're listening for the faint radio whispers of neutral hydrogen with HERA. And now we're even venturing into the realm of dark matter. It seems like we're attacking this photon budget crisis from all angles.
We are.
And I love it.
It's a multi-pronged approach.
It is.
That's the beauty of science.
It is. Before we go any further, I think it's time for a quick recap
Sounds good.
to make sure we haven't lost our listener in the cosmic dust.
Let's do it. All right, so we're trying to solve this photon budget crisis, right?
Right. We know the universe went through this period of reionization, but the amount of ionizing radiation we've observed so far doesn't quite explain how quickly it happened.
It's like we're missing a key ingredient.
Exactly. And we've talked about a couple of ways scientists are trying to find that missing ingredient, like searching for the faint signal from neutral hydrogen.
The 21-centimeter signal.
Right. And those efforts have led to even more intriguing questions, like the unexpectedly cold hydrogen detected by the EGS experiment.
Which could point to some really mind-blowing new physics.
It could. So it's clear that we're just starting to scratch the surface
Yeah,
of understanding this crucial chapter in the universe's history.
absolutely. And there's another tool
Yeah.
that we can use
Okay.
to study the early universe.
Oh,
Quasars.
Quasars, I remember those from the article.
Yeah.
They're like,
Cosmic lighthouses.
okay, yeah, break that down for our listener.
So imagine you've got a supermassive black hole,
Okay,
millions or even billions of times the mass of our sun,
yeah,
surrounded by this swirling disk of gas and dust.
like a cosmic whirlpool?
Yeah, with a black hole at the center.
Okay,
And as all this material spirals inwards towards the black hole, it gets superheated, and it blasts out these incredible amounts of energy across the entire electromagnetic spectrum.
so we're talking radio waves, X-ray?
Yeah, the whole shebang.
So these things are bright,
They are incredibly bright.
even from billions of light years away.
Exactly, and that's what makes them so useful for studying the early universe.
So we're using them to look back in time.
We are.
Okay, but how do quasars help us understand something like the epoch of reionization?
Well, remember how we talked about neutral hydrogen absorbing certain wavelengths of light?
Right, like it has its own fingerprint
Exactly.
in the light spectrum.
So as the light from a quasar travels towards us, it passes through clouds of gas. And that includes any neutral hydrogen that hasn't been ionized yet.
Okay, so if we see those specific wavelengths missing,
Yep.
It means there was neutral hydrogen in the way.
It's like the light is carrying a record of everything it's encountered on its journey.
It's like cosmic archaeology.
I like that.
We're digging through layers of light to uncover the universe's past.
And it gets even cooler.
Oh, there's more.
Quasars might even help us track down those very first stars.
The ones that kick-started cosmic dawn.
The ones that started it all.
But how can we even tell if a star formed from that primordial material?
By their chemical makeup?
Oh, so they have a different chemical signature.
They do. So stars are like these giant factories.
Okay.
They're constantly creating heavier elements through nuclear fusion.
Right. Hydrogen fuses into helium into carbon,
That's it.
and so on.
And as stars live out their lives and eventually die, they scatter those heavier elements out into space. And that gets incorporated into new stars.
So over time, stars kind of add more and more ingredients
That's a good way to put it.
to the cosmic mix.
And it's those heavier elements that give us clues about a star's origins.
So if we find a star that's mostly hydrogen and helium, with very few of those heavier elements,
It probably formed early on, before those elements became widespread.
like a vintage bottle of wine,
Yeah.
a taste of the early universe.
And that's what makes quasars so exciting. Because if their light passes through a cloud of gas that's been enriched by the first stars, we might see traces of those early elements.
In the quasar's light?
Exactly.
That would be incredible.
It would be like finding the missing pages of the universe's baby book.
I love these analogies. Okay, so we've got JWST giving us these amazing images. We're listening for the faint radio signals of neutral hydrogen with Hera, and now we're using quasars to hunt for the first stars.
We're leaving no stone unturned.
It's like we're putting together a giant cosmic puzzle.
And we're starting to see the bigger picture.
We are, but speaking of the future, what's on the horizon for this field?
So there's this project called the Square Kilometer Array,
Okay, the SKA.
or SKA for short.
I've heard of this.
Yeah, it's going to be huge.
Like the biggest radio telescope ever built?
The biggest one ever.
Okay, so what kind of impact is that going to have?
Well, it's going to be sensitive enough to map the 21-centimeter signal across the entire sky.
The entire sky.
That's half the volume of the observable universe.
Wow, that's a lot of data.
It's going to be a huge leap forward for our understanding of the epoch of re-innovation.
So the SKA is going to be here on Earth.
Right.
But are there any plans to put telescopes in space?
There are some pretty wild ideas out there.
Oh, like what?
People are talking about building radio telescopes on the moon.
On the moon? Why the moon?
Well, because it's quiet up there.
What do you mean?
No radio interference for Earth.
Oh, right.
So we could potentially detect even fainter signals from even further back in time.
So it sounds like the quest to understand the epoch of reionization is just getting started.
It is. There's so much more to discover.
I agree. All right, well, we've covered a lot of ground here, from quasars to future telescopes. So let's do a quick recap,
Okay, sounds good.
just to bring it all together for our listener.
Let's do it.
All right, so we've been talking about this photon budget crisis and all these incredible ways scientists are trying to solve it.
We've covered a lot of ground, yeah.
We have from the James Webb Space Telescope to these giant radio telescopes like Hera.
And even quasars.
Oh yeah, quasars, those things are mind-boggling.
They really are.
It's amazing how we can use these tools to study something that happened billions of years ago.
It is. It's like we're time travelers in a way.
Using light and radio waves to peer back into the universe's past.
Exactly. We're piecing together this cosmic puzzle one observation at a time.
But even with all these incredible advancements, there's still so much we don't know.
Oh, absolutely. The epoch of reionization is still full of mysteries.
Like how those supermassive black holes formed so early.
Yeah, that's a big one.
And what role dark matter might have played in all of this.
Right. Those are questions that will keep scientists busy for generations to come.
I can imagine.
But that's the beauty of science, isn't it?
What do you mean?
It's a never-ending journey of discovery.
It is. There's always something new to learn, something new to explore.
Exactly. And that's what makes it so exciting.
I completely agree. So we've gone from a simple concept like reionization to this wild ride through universe-breaker galaxies, supermassive black holes, the hunt for the 21-centimeter signal, and even the possibility of exotic dark matter interactions.
It's been quite the adventure.
It has, and I think it's safe to say that the quest to understand this era in the universe's history is far from over.
Oh, it's just getting started.
Well, I, for one, am excited to see what new discoveries await us.
Me too. And who knows what the future holds?
Maybe one day we'll even have those radio telescopes on the moon.
That would be incredible.
It would, and we'll be right here to cover it all.
Sounds like a plan.
So thanks for joining us on this deep dive into the epoch of reionization. We'll see you next time for another exemption through the cosmos.
CT2.